Okay, so now let's do question number 9, which is show that each of the relation R in the set A given by this is an equivalence relation. Find the set of all elements related to one in each case. Well, the question is not very straightforward, but let's break it down. So you want to show that each of the relations R in the set A given by these two are equivalence relations. So exercise number 9 is you want to show that basically both the relations R is equal to all the order pairs A comma B such that the absolute value of A minus B is a multiple of 4 and also R is equal to all the ordered pairs A comma B such that A is equal to B, that both of these relations in the set A is equal to basically X belongs to Z such that 0 is less than or equal to X less than or equal to 12. So both of these relations are equivalence relations. And find the set of all elements related to one in each case. Also find the set of all elements related to one in each case. Okay, so in order to solve this problem, so first of all you want to show that basically each of these relations in this set is an equivalence relation. So we have a couple of things to do, meaning that it's actually two exercises in one exercise. So let's do that. So I'll make a screenshot here so that we can use this later. And so let's get started with this. So first of all, I'm going to consider basically R is equal to A comma B, or the order pairs A comma B such that the absolute value of A minus B is a multiple of 4, and I'm going to consider the set that we have, which is X belongs to Z, such that 0 is less than or equal to X less than or equal to 12, right? And I want to show that R is an equivalence relation. So in order for R to be an equivalence relation, it has to be a reflexive relation. It has to be reflexive, it has to be symmetric, it has to be transitive. So reflexive So in order to show that R is reflexive, we need to show that basically A comma A belongs to R for all basically A belonging to A. So we need to show that basically A comma A belongs to R for all A belonging to A, right? Belonging to A. And now if basically well, of course, A comma A is a multiple of 4. Okay, so let's say that, so first of all, let's write down this set A over here. A basically, based on the definition of this set, is equal to 0, 1, 2, 3, all the way up to 12, right? Which means that R is going to be basically the set of all of these ordered pairs, such that A minus B is a multiple of 4, right? Now, if I take 0 with 0, for example, then 0 minus 0 is equal to 0 minus 0 is equal to 0, which is a multiple of 4. 1 minus 1 is a multiple of, is 0 again, a multiple of 4. 2 minus 2 is a multiple, and so on and so forth. So then you can say that basically A comma A belongs to R for all A belonging to A, and the reason for that is that basically the absolute value of A minus A is equal to 0, which is a multiple of 4. So what that means is that then R is reflexive. R is reflexive. To show that R is symmetric, we need to show that basically if basically A comma B belongs to R, that implies that B comma A also belongs to R. If that is the case, then basically we can say that R is symmetric. So of course, now suppose that, for example, some A comma B belongs to R basically. That implies that the absolute value of A minus B is a multiple of 4, right? So that is a multiple of 4. Now, and that implies that basically the absolute value of B minus A is also a multiple of 4, because the absolute value of A minus B is actually equal to the absolute value of B minus A. They are the same value, so there is no difference between the two. And so basically the absolute value of B minus A is also a multiple of 4, which means that basically the ordered pair B comma A does belong to R. So the ordered pair A comma B belongs to R, the ordered pair B comma A belongs to R, which means that basically R is symmetric. R is symmetric. Now the next thing that we have here, we want to show that R is transitive. R is transitive. So to show that R is transitive, you need to assume that some x comma y and y comma z belong to R, and then that has to imply that x comma z also belongs to R. If that is the case, then you can say that R is transitive. So now let's assume that some x comma y, and some y comma z belong to R. If I make that assumption, what that means is that the absolute value of x minus y is a multiple of 4, and the absolute value of y minus z, is a multiple of 4. Now, so what that means is that I can write x minus y as basically 4 times m, for example, for some integer m, right? Since this is a multiple of 4, I can write it as 4 times m. And since this is also a multiple of 4, I can write y minus z as 4 times n, for example, for some integer n. Now how can we show that basically x and z belongs to R as well, meaning that x and z are basically again multiples of 4, meaning that the absolute value of x minus z is also a multiple of 4. So if you take these two equations and add them together, I get x minus y plus y minus z is equal to 8m. I'm sorry, not 8m, but it's equal to basically 4m plus 4n. And if I cancel these two out, I'll get x minus z is equal to 4m plus 4n, which means that x minus z is equal to 4 times m plus n. And since these two are integers, we agreed that over here m and n are integers. I can write this as x minus z is equal to 4 times, for example, r, for some integer r. Which means that basically x minus z is a multiple of 4. Which means that basically x comma z, okay, so over here we said that so if x minus z is a multiple of 4, based on this I can write basically the absolute value of x minus z is also a multiple of 4, right? That is, there is nothing wrong with that. There is a multiple of 4, which means that if the absolute value of x minus z is a multiple of 4, based on our r over here, we said that if the absolute value of a minus b is a multiple of 4, then a comma b belongs to R, right? That does belong to R. That means that x comma z does belong to R. Now over here we argued that basically x comma y and y comma z belong to R, and over here we concluded that the x comma z also belongs to R, which means that basically R is transitive. R is transitive. So over here we showed that R is reflexive. Over here we showed that R is symmetric, and over here we showed that R is transitive. That means that R is an equivalence relation, right? So that is about one part of the problem. Now the second part of the problem is that I have the same set here, A, which is basically this set over here, but this time the relation changes. So the relation is all the ordered pairs a comma b, such that a is equal to b, right? So what we have now is that basically the set a is equal to x belongs to the set of integers such that 0, I'm not sure if that was 0. Yes, 0 is less than or equal to x less than or equal to 12. That means that a is the same thing as 0, 1, 2. I'm not sure if we did the right thing here. Yes. Okay. So 1, 2, 3 all the way up to 12. And the relation that we had was basically R is equal to the ordered pairs a comma b such that a is equal to b, right? So what that means is that you can write this set R as basically 0 comma 0 and 1 comma 1 and 2 comma 2 and 3 comma 3 and 4 comma 4 and 5 comma 5 and 6 comma 6 all the way up to 12 comma 12. That is the set R, which means that then we need to basically simply show that basically R is an equivalence relation. So let's see how we can do that. Okay, so now let's decide whether R is an equivalence relation here. So basically of course you can see that R is an equivalence relation because you can say that basically a comma a belongs to R for every a belonging to A, of course. You can see that 0 through 12 and then 0 comma 0, 1 comma 1, 2 comma 2, 3 comma 3 and so on and so forth are all belong to R. So you can say that R is basically reflexive. Moreover, to show that basically to show that R is symmetric, you need to show that basically if A comma B belongs to belongs to R, that implies that B comma A does belong to R as well. That's the condition. Of course, for all A and B belong to, for all A and B, for all A and B belonging to A, right? So since all of the members of R are just, since all members of R are in the form A comma A, for all A belonging to A, then the condition 1 is already fulfilled. It's already fulfilled. And so you can say that basically you can say that R is symmetric. What that means is that, for example, if you imagine that, for example, if you imagine that 0 comma 0 belongs to R, then you can argue that again. Basically, if you say that x comma y belongs to R, then for R to be symmetric, y comma x has to belong to R as well, right? Now, since over here I have in all of these basically in all of these x comma y is x is equal to y, then you can say that basically then you can say that for all of these x comma y's, then y comma x also belongs to R. So for example, for 0 comma 0, you can argue that 0 comma 0 again belongs to R, and so what that means is that you can say that basically R is symmetric. R is symmetric. For R to be basically transitive, the condition is that, let's suppose that some x comma y and y comma z belongs to R. That has to imply that x comma z also belongs to R. Let's call it condition number 2. Now, if that is the case, then let's suppose that, for example, now here the problem is that I cannot basically make this assumption in the first place. That means that, let's see, let me take a look at the solution here. Number 1 and number 2. Okay, so the solution here is simple. Let's assume that basically some x comma y and y comma z belong to R, right? Let's assume that x comma y and y comma z belong to R. Now x comma y belongs to R. If that belongs to R, that implies that x is equal to y. And y comma z belonging to R implies that y is equal to z. So that implies that y is equal to z, which if y is equal to z, that implies that basically or you can say that x is equal to z. You can also say that x is equal to z. Of course, there is no need to write this in here. So you can say that since x is equal to y, y is equal to c, so that means that x is equal to z. X is equal to z. And if x is equal to z, then that means that x comma z also belongs to R. So here we have x comma y and y comma z belongs to R, and here we have concluded that basically x comma z also belongs to R, which means that basically R is transitive. R is transitive. And so what that means is that basically R is transitive, is symmetric, is reflexive, and so R is an equivalence relation. R is an equivalence relation, right? So now the second part of this question, we want to, so basically here we said that we wanted to show that basically both of these relations in the set A are equivalence relations, which we already did, and we want to find the set of all elements related to 1 in each case. So the set of all elements related to 1, so how do we do that? So we need to see which of these elements are related to 1. I mean, let me actually erase all of this. So now suppose that, for example, I consider, for example, the set A, which is equal to x belonging to z, such that 0 is less than or equal to x less than or equal to 12, which means that A is equal to basically 0, 1, 2, and so on and so forth, all the way up to 12. And let's say that R is basically, let's call this 1, and let's call this 2, for example, and let's just say that basically R is equal to all the ordered pairs A comma B, such that the absolute value of A minus B is a multiple of 4. Is a multiple of 4. Now, how do I find all of the elements? How do I find all of the elements related to 1? So, in order to do that, what I can do is that all of the elements related to 1 would be, okay, so basically, as you can see, in the case of this set, we have 0, 1, 2, and so on and so forth, all the way up to 12. And we want to find basically, we want to find all the elements basically in A related to 1, right? So what that means is that basically the element 1 is related to that element in A under R, right? Which means that basically the difference of one and the other element has to be a multiple of 4. So if I go, for example, with 0, if I go with a 0, for example, the absolute value of 0 minus 1 would be equal to 1, which is not a multiple of 4. If I go with the 1 over here, so 1 minus 1 is equal to 0, which is a multiple of 4. If I go with the 2, 2 minus 1 is equal to 1, which is not a multiple of 4. And if I go with a, for example, a 3 minus 1 is equal to, for example, 2, is not a multiple of 4. If I go with a 4, then 4, the absolute value of 4 minus 1 is equal to 3, which is not a multiple of 4. If I go with a 5, the difference of the two would be equal to 4, which is a multiple of 4. And so as you can see, all of the elements in A, that you can see that basically all of these elements that are even numbers, meaning that, for example, over here or over here, none of these even numbers is related to 1, because we said that the difference between an even number and an odd number and an odd number is always basically an odd number, which is not what we are looking for. So what we are looking for is that the difference of those two numbers is supposed to be a multiple of 4, which is an even number. But not just an even number, an even and a multiple of 4. And a multiple of 4. That means that if I say that, for example, a number is if I say that a number is an even number, that number is a multiple of 2, right? But then over here, I need 2 factors of 2 so that the number is an even number, and also so that the number basically is an even number and also has 2 factors of 2 so that it becomes a multiple of 4. So that means that in all of these numbers that I find here, first of all of the even numbers I have to discard, meaning that I write, for example, some set B as basically 1, 3, and 5, and 7, and 9, and 11, and 13. So 13 doesn't really exist there. So I write this as basically 9 and 11. These are all the odd numbers that I have. Now I need to be looking for numbers in this set whose difference with 1 becomes a multiple of 4. Of course, the 0 is also there, right? I'm sorry, 0 is not there. 0 is an even number, right? So what that means is that, for example, 1 minus 1 is equal to 0, so 1 is there. 1 is there. 3 minus 1 is equal to 2, which is not a multiple of 4. 5 minus 1 is equal to 5 minus 1 is equal to 4 is a multiple of 4. 7 minus 1 is equal to 6, not a multiple of 4. 9 minus 1 is equal to 8, a multiple of 4. And 12 is also a multiple of 4. So the set that we are looking for, C for example, is 1, 5, 9 and 11. 1, 5, 9 and 11. I'm surprised to see that 11 is not actually in the solution. Let me see. Well, that is of course correct, because 11 minus 1 is equal to 10, which is of course not a multiple of 4. So then you can say that the numbers that you're looking for, 1, 5 and 9, are the numbers related to 1 under R. So basically we understand what that actually means. Now in the second part of this question, we also need to find basically the numbers related to 1 using the other relation that we had, right? So again, A was equal to 0 through 12. So again, basically we said that A was equal to 0 to 1, 2 and all the way up to 12, and the relation that we had was basically all the order pairs x comma y, such that x is equal to y. So what that means is that if 1 is supposed to be equal to 1, if 1 is supposed to be related to 1, then there is only one possibility here, and that is basically a set containing only 1. Only 1 and 1 are related to one another under this relation, right? So that is basically question number 9. Right? Now in the next video we'll talk about question number 10. I'll see you in the next video.